So today we'll talk about the chapter 2 electromagnetism for EET 208 electrical power technology. So why we study electromagnetism or electromagnetics? Electromagnetics is the fundamental to the advancement of electrical and computer engineering technology. So electromagnetics is used to generate electricity, store memory on our computers, generate pictures on a television screen, diagnose illnesses. Examples of this, for example, the 4G, 5G communication technology, all that involve electromagnetic wave. We have a CCTV. This is some sort like iPod, telephone, monitor. So definition of electromagnetism. Electromagnetism is the branch of science. Electromagnetism is a science, branch of science that concern the forces that occurs between the electrical charged particles. So when we talk about electromagnetism, it is a science actually. Then what is involved? It is involved force. It involves the force that generated by the electrical charge particle. So in electromagnetic theory, these forces are explained using electromagnetic field. So we have several magnetic materials. For example, permanent magnet. It is a magnetic material that can retain its magnetic characteristic. So, for example, a mixture of aluminum, nickel, cobalt, and iron. We have also a temporary magnet, a material that has a magnetic characteristic at certain conditions. For example, soft iron, iron alloy. Then the pointer of a compass is called as a permanent magnet. For example, in a compass, you like to see the north and the south. Then because it always retains its peculiar properties, it's suspended in a horizontal plane. So the Earth North Pole and the other end will be called as a South Pole. Definition of magnetic field. So magnetic field is an area surrounding a magnetic material that has the effect of magnetic force. For example, this line, all are considered as magnetic field. So it is an area. So this area surrounding a magnetic material. This is the material that has the effect of magnetic force. Which means if let's say I put something here, we can feel that the magnetic force. So this is called magnetic field. The curved chain between the pole can be seen in the figure. Curved chain like this. Actually it's this one, curved chain. Or here. So the shape and density of this change shows the magnetic condition of space or the field around a bar magnet. We call it as a magnetic flux. So this we call magnetic flux or outwards. Even though it is not enclosed, but it is called magnetic flux. So two poles dictated by direction of the fields. The lines of magnetic flux are assumed to pass through the magnet, emerge from the North Pole and return to the South Pole, which means the line will go to the South Pole and then emerge inside the magnet, then go out again, then from the North Pole, then go in again from the South Pole. So opposite pole attract or align magnetic field, same poles will repel opposing magnetic field. So attracting field from north and the south, it will align and attract each other. For the poles which repel, the north and the north pole, this line will push the other line from here. Then the direction of magnetic field. Electromagnetism works on the principle that an electric current through a wire will generate a magnetic field. It's very simple. Magnetism works where when there's electric field, electric current flowing through the wire, then there will be magnetic field around it. This is called electromagnetism, where we change the electromagnetism word. We will know from itself, electromagnet. We change the electrical side to magnetic side, or we change the magnetic side to electrical side. So that's why we call electromagnetism works on the principle that an electric current. So electric current flow through the wire, it can generate the magnetic field. So in a bar magnet, the magnetic field runs from the north to the south pole as usual. In a wire, the magnetic field forms around the wire. For example, this one. When there's a current flowing through in the wire, so we will see the magnetic field surround it. For example, like this. When there's a current flowing through, then there will be a flux or field surround it. But how can we determine the value, the direction? We actually use a right-hand rule. So a method of representing the relationship between the direction of a current and magnetic flux, or the direction of the magnetic current, the current and also the magnetic flux. How? We use Fleming right-hand rules. So we grab around the wire, then the current will go up, then the magnetic direction of the magnetic field created will around our fingers. So if the current is flowing towards us, it will indicate it as a dot arrow. If the current is flowing away from it, will represent by a cross, equivalent to the departing tail feathers of the arrow. Just a simple illustration, if this is an arrow, if we look from here, which means the flux is coming to us, so we will see a dot here. If we look from here, we will see the flux flowing through towards the other side, outwards from our eyes, we will see the tail of the arrow, which is cross. So right hand rules, yes, we explained before. Thumb indicates the direction of the current flow. Finger curl indicates the direction of the field. Okay, then we'll go to electromagnetic induction. Just now is a basic of electromagnetism. Now we want to study how it's related. Okay, how's the operation of the electromagnetic conversion? So electromagnetic induction is the production of an electric current across a conductor moving through a magnetic field. So just now we talked about electromagnetism. Electromagnetism is something like there's the conversion between the electrical side to magnetic side, or magnetic side to electrical side. So we call it as there's a few forms. One of it we call it as a induction form. That's why we start from the most simple one. We start from the electromagnetic induction, where we produce the electric current when there's a conductor passing through the magnetic field. So we have electric current, we have magnetic field, and then we have a conductor, three things. So the process of generating current in a conductor by placing the conductor in a changing magnetic field is called induction. This is called induction because there is no physical connection between the conductor and the magnet. Then the current is said to be induced in the conductor by the magnetic field. So inductions, there's no physical connection between the conductor and for example, this one. When the line is going up and in, cutting through the fluxes that are generated by the magnet, there will be electric current passing through. There's no physical connection between the wire and also the magnet. So that's why we call induction. So, put it in a proper way of a saying of this induction, we call it as a force on a current carrying conductor. If you still remember the previous slide, electromagnetic induction involves three things. One is electric current, one is conductor, one is magnetic field. So before we talk about the force on a current carrying conductor, we need to know about the cross product and the dot product. So the cross product is, for example, we have a vector A and vector B. So the cross product of A cross B is defined as a vector C. So this is the vector C, A cross B. So C is perpendicular or orthogonal to both A and B. A and B. And then C is orthogonal. And then with the direction given by the right hand rules. Okay, show your right hand rules like this. So if I say this is A, this is B, then our C will be going up. Then the magnitude equal to the area of the parallelogram. This is area of the parallelogram that the vector spun. So the formula becomes vector A cross vector B equals to magnitude of A times magnitude of B and a sine theta. So this is the cross product. Okay. So so we can see that for example, this is A and B, and then when it's turned around, when it is in line, so it is sign 0. When sign 0 is 0, no? Then yeah, A cross B when sin 90, this is A, for example, this is A, this is B, so sin 90, then it will be 1, so A cross B sin 90 is 1. Then sin 180, it becomes 0, okay, sin 180 becomes 0. Sin 270 or sin negative 90, it becomes 1 again. So this is how but in negative direction, negative, because sin negative 90 should be negative 1. So let's have a look again. So this one will be 0, then it will be positive. Okay, sin 90 is positive 1, then sin 180, then sin 180 will be 0 again. Okay, so A cross B will be 0. Then sin negative 200, sin 270 or negative 90, it will become negative 1. So A cross B as well, but it is in negative direction. So this is the definition of A cross B lah. We need to use this one in current carrying conductor. Another one is a dot product. So algebraically, the dot product is the sum of the products of the corresponding entries of the two sequences of numbers. Very simple is A dot B, A times B to get the algebraic product. It has two things. One, it can be defined as algebraic, or another one is geometrical. Our case in geometrical. So geometrically, it is the product of Euclidean magnitude. This is Euclidean magnitude, of the two vectors and the cosine of the angle between them. So when we talk about A dot B, actually we need to find this length times this length. So how to find this length is A, this is hypotenuse, A times this cos of this angle, we have this length. And then we times this length, B. So it becomes our dot product. So we need to know cross product and dot product so that we can use it later. Field. So come back to here. One is conductor, one is current, electric, one is a force. So force actually is something like we need to cut the moving the conductor so that it can react with the magnetic field. So two permanent magnets rest on, for example, this one. Two permanent magnets rest on the sheet of the paper. This paper we call as a G, and steel pole pieces P. This one, steel pole pieces P are added to increase the area of the magnetic field in the gap between them. Later I will show you the 2D one. And then this wire will cutting through the paper. Okay, midway between the pole piece is a wire W, passing vertically downwards through the paper G and connected through a switch to a battery. So next, for example, now if my eyes look from the top to the bottom, from the top so we will see this one. So N, North Pole, South Pole, South Pole, South Pole, South Pole, North Pole, North Pole. Then this is just to enlarge the area of the magnetic flux. So we know that the North Pole will flow out and connect to the South Pole, right? And then this is our conductor. So if the switch is closed, this switch is closed, I mean we connect to a battery. Just now, if it is open, there's no current. If it is closed, so this will have current. So the lines of the magnetic flux distort partially surround the wire. Distort means, for example, the line should go through, but because of there's a current passing through the conductor, the line is distorted like this. It becomes bended. Distorted means bended. So the lines of the flux try to return to the shortest path between P and P. This P and P. They are trying to return to its original state. Thereby, they exert a force F urging the conductor. So now going in means this conductor having a current flow towards the paper. That's why from the arrow I flow towards to the paper. So when flowing towards the paper, we use right hand rules. The current is going inside, then the flux will go to surrounding as a clockwise direction. Okay, when it is clockwise direction, it will distort this line. It become like this. And very naughtily, this line are trying to put back into their original state. So that's why what they need to do is they will exert a force, pushing this, go, hey, this fellow, go away, don't disturb my magnetic field lines, so that I can get back to my original state. So we can see a lot of fluxes here, less fluxes here. Then it will try to push down the conductor so that it becomes to this state back. Okay? That's why we call force on a current carrying conductor. So first we need to have a conductor. Second, it must have a current. Third, we will predict that it will have a force. So, well, we would like to put in equation or engineering terms. So the mechanical force exerted by the conductor always acts in a direction perpendicular to the plane of the conductor and the magnetic field direction. We call it as the direction is given by the left hand rules or left hand rules. Make sure 90 degree here, 90 degree here. So 90 degree, this hand, this finger, and this finger. 90 degree, this finger, and this finger. So how to put in a figure for this one? Mechanical force F is this one. Okay, exerted by the conductor. So this is the conductor. Always act in the direction perpendicular, means 90 degree to the plane of the conductor and magnetic field direction. So where is the plane of the conductor and magnetic field direction? So have a look on the conductor. This is our conductor. Where is our field? This is our field. So the plane of the conductor actually is stated on the direction vector of the current. So this finger, we know that it is pointed as a current. This finger pointed as a B. So the plane of the conductor and magnetic field direction means the B and I plane. So we draw it out this one. This is the plane. So it says that left hand rule says that the force is always 90 degree to this plane. It will not go this way, go that way, but it will go to this way. So in this case, if there's a current passing through the conductor within this field, so B is this field. Direction is this one. Then there will be a force go to upwards. Okay? Then we put in the mathematics. It is force on the conductor where F equals to B times I times L. B times I times the length of the L in this area. Okay? So for example, a conductor present in a uniform magnetic field of the flux B pointing into the page. So pointing into the page, from our eyes it is a cross. Then in this case, the conductor where the current is flowing to the downwards. So the conductor itself with an L meter long and contain a current of the I ampere. So we can predict where is the force will go through. So by using the Fleming left hand rules, so now the B is go inside, the I is go downwards. So our V is go to our right. Our force will go to the right hand side. So we put it into an equation. Actually, F is a vector because it has a direction go to the right side. Equals to I is a current. The direction of the conductor L times B, direction of the magnetic flux density. So the induction of the force in a wire by a current in the presence of magnetic field is the basis of the motor action. Right? When there's a magnetic flux density, when there's a current, then we will have a force. For example, the fan, I switch on it. So there will current inject into the stator coil, which is the coil. Then from the coil, it will rotate the motor. So this is under motor action. We use this equation, Fleming's left hand rules, to calculate it. So for example, a current carrying conductor, the length is 150 cm long, is located at the right angles, to a uniform magnetic field, having a density of 0.3 Tesla. Calculate the force on the conductor when the current is 200 ampere. So very easy, we apply the formula F equals to ILB sin theta equals to 200 is our current, 150 centimeter, 150 times 10 to the power minus 2 is our length, and our flux density is 0.3 Tesla, and then it is sin theta with a 90 degree. We have a 90 Newton. Yeah, another example, a conductor 150 mm long is carrying a current of a 60 amp at the right angle to the magnetic field. So a conductor, this is my conductor 150 mm long, is carrying a current of a 60 ampere at the right angle to the magnetic field. So the force on the conductor is a 3 Newton. This is my F. Calculate the density of the field. So first of all, we need to use an equation. F equals to ILB sin theta. So I have a F, which is 3 Newton. I have an I of a 60 m. I have a length of 150 mm. But I don't have B. And I have a right angle of a sin 93. So I use a calculation. I put in the equation. Then I I get my B equals to 0.33 Tesla. So when we talk about electromagnetism induction, we'll think of the Faraday's law. We have the first law. Whenever a conductor cuts a magnetic flux, an EMF is induced in the conductor. Second law, the magnitude of the induced EMF is equal to the rate of change of flux linkages. So we put in equation. Suppose a coil has an N turns and flux through it changes from an initial value of phi 1 Webers to the final value of phi 2 Webers in a time t second. The initial flux linkages we assume is the N phi 1. Then the final flux linkages will be N phi 2. So there's a changes within that time period. Then we put it in this equation, it will be induced EMF. So E equals to, we factorize, equals to d phi over dt. d phi means the difference of the phi 2 minus phi 1. dt is the difference of the time. So this is the equation of the Faraday's first law and second law. And then where's the direction of the induced EMF? We use Fleming right hand rules. So if the fingers on the right hand rules is pointed in the direction of the magnetic flux, thumb is pointed in the direction of the motion of the conductor relative to the magnetic field. The second finger represents the direction of the EMF. So Fleming right hand rules. This is our magnetic flux field. This is our velocity of the conductor. So if let's say the conductor is moving 90 degrees perpendicular to the magnetic flux, then this is our current induced. The induced current will be equivalent to the induced of the EMF. So for example, if a wire with the proper orientation moves through the magnetic flux field, a voltage is induced in it. The idea is shown in the figure 1, this one. So B magnetic flux is going through this paper, and then the conductor is moving to the right side. So the current will flowing through upwards. So when current flowing through upwards, it is actually a battery, which means when we connect this one to a resistor, so the current will go through to this direction, right? So when current go through this direction, this will be our positive polarity. This will be our negative polarity. And then we will put in the equation where E induced equals to V cross B, the velocity cross the magnetic flux density, and then dot the length of the conductor. Three of them are vector. So we can put in this way. E induced equals to V times B sin theta, then times L cos alpha. For example, figure 1.7 shows a conductor moving with a velocity of 5 meters per second to the right of the presence of a magnetic field. So this is the magnetic field, and then this conductor is moving to the right. The flux density is 0.5 Tesla. This one B is 0.5 Tesla into the page. So into the page, we will see the tail, cross tail of the arrow, and the wire is 1 meter long. what are the magnitude and the polarity of the resulting induced voltage. So we want to find the induced voltage. We use the equation VB sin 90 times L cos 0. So VBL. V is a 5, B is a 0.5, L is 1. Then it is 2.5 volt. Positive at the top of the wire. Another example is the direction of an induced EMF. So for example, in the figure 1.9, example 1.9, where the figure 118 shows a conductor moving with a velocity of 10 meter per second. So the velocity is 10 meter per second to the right in the magnetic field, and the flux density is 0.5 Tesla out of the page. So out of the page it is dot, and the wire is 1 meter in the length. This is 1 meter, oriented as shown like this. So it is 30 degree if comparing to here. What are the magnitude and polarity of the resulting induced voltage? So we will use this formula where Fleming right hand rules. First, it is come out from here. Okay, come out. For example, it is come out like this. Maybe come out like this. Then after that, our velocity is to our right side. Okay, but our conductor, it is not 90 degree towards down, right? It is not 90 degree towards down. So what we need to do is we need to make sure to find the components where the length of the wire can be separated into x and y. This is x, this is y. We need to find in y direction. So B cross B actually is a 90 degree because B is going out from a piece of paper, and then B is to my right. So we can see that it is actually here is 90 degree. Here is 90 degree. Okay. So FBI. Then dot I. We need to find the smallest, the nearest length to this to the y component. So we actually just use a dot product. Just now this is a cross product. Then we use dot product, whereby we use L times cos of 30, so that we find this what we so call the length, the component of this length, to make sure it is all 90 degree. So for example, now the B is going up, B is going to the right side, but my L actually is shift to the like this. Okay, shifted like this. By right, I need to find like this. So what I need to do is I find a component. I use a L times cos theta. This become our component. Okay, so that everything will be 90 degree from each other. Then we put into the equation. Then we found that it is a 4.33 volt. So please indicate the positive and negative terminal. So we will know that this is positive terminal. This is a negative terminal. Then another guy is saying that the Lenz's law, the direction of the induced EMF is always such that it tends to set up an current opposing the motion or the change of the flux responsible for inducing that EMF. So just now we have a VE induced equals to N d phi dt, and then Lenz found that actually we need to put another one is a negative here. It shows that the induced EMF always need to generate to oppose the change of the flux. So for example, if this situation where the North Pole create the flux of B, suddenly it move in. Okay, so when it move in, the flux will increase by changing in this direction. And then the Lenz law saying that the coil must be created, the induced EMF, where it will oppose the changes. So now we want to create the in order to create the opposing induced magnetic flux density, where is the direction of the current need to induce here? So we use we use right hand rules, going like this. So we know that going like this, so the current will flowing downwards like this, so that it will create the magnetic flux, this one, magnetic field in this direction to oppose the changes here. So what if when the pole need to go out from here? So the original, the flux is in here, in this line. So if let's say the magnet is moving outwards, which means there's a changes of the magnetic flux density. And then, according to the Lenz's law, this circuit need to create the magnetic flux that can oppose these changes. So how to create is we use a right hand rules, okay, like this. We will create a magnetic in this way to the left, okay, so that to oppose the changes. This is Lenz's law. Same happened to the south pole, okay. I mean in this scenario. So for example, now I have a flux going topwards, going to the top, okay? And then we need to know where is the direction of the induced EMF or the current. So very easily, I need to create the induced EMF need to create so that it will oppose the flux here. So how to create the flux oppose here? Okay, we will create like this one. Okay, where the current will go to like this way. This is called direction of the induced EMF. So thank you very much. Hope you enjoy the slides.